Hi there, welcome back again to this course in ABE161, and this video will be moving on to our next topic, which is the singly reinforced beams. So this is actually our first topic that we deal with a specific structural members, and we'll talk about the designs, then the designs or analysis, and even the code provisions that that governs the analysis and the design of such structural members. So for now, we'll talk about beams, and then the succeeding weeks we'll be talking about, let's say, the columns, and then the footings. Then after that, we'll talk about steel structures. Okay, and then finally, we'll be discussing the timber structures. Okay, so for now, we'll just talk about the singly reinforced beams. Recall that beams are structural members that, when subjected to, okay, so recall that, for example, these are beams that, when it's subjected to, let's say, flexural loads, right? So let's say we have a flexural loads here, could be distributed um, or concentrated. Okay, so when you have these flexural loads, what you get is actually a shear and moment diagrams. Okay, so because of these external loads or external flexural loads, then we get an internal shear. So take note, can this is an internal force. So we have an internal shear, and then we'll have an internal moment. Okay, so in this shear and moment diagram, we get a maximum value. Okay, so let's just say V max. That could be negative or um, positive, but the point here, what you get is there's going to be a V max. And then for the moment or internal moments, we'll also get a maximum moment. So let's say M max. So that could be positive or negative. So just a brief overview. When we talk about reinforced concrete structure, recall that the tension zone actually matters. So the location of tension zone matters because that's where we put our tensile reinforcements. Okay, so that depends upon your boundary conditions and your loading conditions. But for now, let's just say we'll just consider this that this M max value. Okay, the point here is whenever there's a loadings, then there's gonna be some M max. Okay, and these values, they're actually the ones that we're using in the loadings or in the load transfers. Okay, so for reinforced concrete, we have to design, or let's say the configuration of the beam must be able to withstand these loadings. Okay, so recall that for RC beams, we have a main reinforcement. Okay, so when you say main reinforcement, then that's gonna refer to the flexural reinforcement. Okay, so that's the reinforcement for these internal movements. But there's another reinforcement that we'll be designing. Um, this is what they call the stirrups. Okay, so this one, the stirrups, are designed for shears, whereas the flexural reinforcement are designed for these internal moments. Okay, so this is just the basic. Again, the location of this flexural reinforcement, that depends with, let's say if you're a cantilever beams, then your flexural reinforcement will be at the top. Okay, so um, we'll talk now the different types of RC beams because you can have also, if you recall that I've mentioned during the introduction to reinforced concrete that you can also provide reinforcement in the compression zones. Let's say, for example for in columns. So even though concrete is strong in compression, but we still add compression reinforcement. So the same goes true with some beams. So sometimes beams are designed uh, that the compression reinforcement. Sometimes beams are designed to have a compression reinforcements. Okay, so let's now go through over the different types of RC beams. Okay, so number one, we have a singly reinforced beams. Okay, so when we say singly reinforced beams, reinforcement is only at the tension zone. Um, the tension, okay, zone. Okay, so if we illustrate this, it's just like this. Okay, so this is the reinforcement. Okay, so that's the one that we're designing. The size or how many rebars are we going to put in that section. Okay, so um, another type of beam is what we call the doubly reinforced. Okay, doubly reinforced. Okay, let's just write number two, beams. So meaning that the compression zone has also reinforcement. Okay, so take note that in construction, even though the beam is designed to be reinforced, a singly reinforced, you'll also notice something like this. Okay, so let's say this is a singly reinforced beams, but then you'll also notice another, or the presence of the two top bars here. And then we have the stirrups. Okay, so these two top bars, they're not actually designed as reinforcements. So when we say singly reinforced, then meaning that the the reinforcement is only on the tension zone. Okay, so this is the reinforcement, whereas the two top bars here, they're called hanger bars. Okay, hanger bars, that's where the stirrups are attached to. Okay, so the, again, the difference is the reinforcement. If we're designing it to be reinforced in the tension zone, then that's going to be singly reinforced. But if we take into account the, let's say the top bars, let's say we take into account the capacity provided by the top bars, then that's going to be a doubly reinforced beam. And then number three, we have a T-beams or L-beams. Okay, so T-beams or L-beams, basically, it happens when a portion of, or when you cast monolithically the beams and the slabs. Okay, so meaning that you pour the concrete mix into this slab formworks and then the beam formworks, and then the sets, let's say they sets together or they sets at the same time. So meaning because of that, something like extra bonding between the beams and the slabs, then you're gonna have some extra capacity of this slab portion. Okay, so a T-beam happens when, of course, it's gonna be let's say an interior beam. Okay, so let's say we have a slab on top. Okay, so this is the slab. Okay, so let's say this is slab, and then this is your interior beam, and then this is your exterior beam. So because of the monolithic, let's say, action, then it's gonna provide something like an extra flanges, right? So from this point to this point, then this gonna contribute to the capacity of the section. Okay, so that's why they call it a T-beam. Okay, so for the exterior, it's gonna be an L beam because it shapes like inverted L. So the T beam can also be designed singly reinforced or doubly reinforced. Okay, so that depends whether you want a compression reinforcements or a tension reinforcements. Okay, so in this course, we're only gonna tackle these singly reinforced beams. Okay, but at least I have introduced you to these two concepts. Okay, so in this topic, the singly reinforced, we can classify the problem as, let's say, analysis problem. Okay, so when you say analysis problem, then you're given the geometry of the beam, you're given the sizes, and then you are to find the capacity. Okay, so that's the analysis problem. And then for the design problem, we'll have a, you're given a loads, and you have to determine or you have to find the geometry of the beam or the let's say the size of the rebars and stuff like that. How many rebars? So the design problem, we're not gonna tackle this. Only the analysis. Okay, so but for these design problems, there's still two types. Like for example, a known cross section. So in this problem, you have um, a geometry of the beam, except that you don't know how many rebars you are going to put in. Okay, and then um, another type is unknown cross section. So this is kind of probably more difficult, or because you have to make some assumptions and things like that. Okay, so unknown cross sections. Okay, so meaning you don't know, you really don't know this, let's say the beam width or the number of steel reinforcement. But for here, what you don't know is the steel area. Okay, so again, in this course, we'll only talk about the analysis of singly reinforced beams. Okay, so now let's talk about the nomenclature for singly reinforced beams. Because when we deal with calculations, then we're gonna have some terminologies regarding this beam cross sections. Okay, so let's have this example. We have three reinforcements, then we have hanger bars on top. Okay, so again, this is singly reinforced. Now the distance from this edge to this edge. Okay, so that's what we call the beam width, right? So let's just write it here, beam width. Okay, and then the distance from this top, let's say top face to this bottom face, that's what we call the total width. Okay, so that's h. No, no, sorry, not total width. I mean total height. Okay, so that's we'll use the symbol h, and then you notice that we'll have two layers here. So the design actually depends if you want a two layer or single layer. But the point here, if we have two layers, then we need to have a centroid. Okay, so basically that's just the midpoint between these two. So if you have the same sections, I mean same diameter of bar, same area, same numbers, then the cross section, I mean the centroid would just be at the midpoint. Okay, so from the centroid to this top face, that's what we call the depth. Okay, so depth, or some um, some reference, that's the effective depth. Okay, and from this, okay, so since we have two layers, so the outermost steel member, so that's actually D, the depth, subscript with letter T. Okay, so that's the extreme tension steel. Okay, so extreme tension steel. Okay, so Then we'll have the distance, the clear distance between bars. Okay, so the clear distance between bars, that's subscript as S sub B. Okay, so spacings or spacings. Okay, so um, um, that also holds true if we mean this distance from the bottom bar to the top bars. Okay, so that's gonna be the S sub B. Okay, so with regard to S sub B, there's got the code requires that we have a minimum of um, okay, so S sub B mean is equal to bar diameter or greater than 25 mm. Okay, so that's going to be our bar spacings. Okay, what else? Then the distance from this, let's say, this face of of steel reinforcement to this bottom face, that's what we call the concrete cover. Okay, so concrete cover, it's actually protection to the steel reinforcement. Okay, so probably um, let's say if you have something like it is a protection to your steel reinforcement, like for example, protection from environmental conditions. Like for example, your concrete is cast and permanently exposed to earth. So we have a table there in our lecture handouts that's 75 mm. So if exposed to earth or weather, and depending upon the diameter of the bar, we have 50 mm and 40 mm. And for slabs, walls and beams, okay, so for slabs we have 20 mm, and then beams and columns we have 40 mm. So meaning, that example, this is a beam, let's say a roof beam or a floor beam, elevated floor beam, then we have a 40 mm minimum concrete cover. Okay, so it's also possible to have a bundled bars, like for example, you have to bundle, say, two bars or something. Okay, so that it just something like it acts like a single layer. So you can do so. So that's what we call the bundled bars. Okay, and then stirrups. This is the ones that we attach it here. So the stirrups, the ones designed for shear, internal shear, whereas this main reinforcement, this is for tension or tensile stresses. Okay, so now let's move on to the behavior of beams under flexural loads. Okay, so consider a beam under 2-point loadings. Okay, so let's say we have support here. So if we draw the shear and moment diagram, what we get here is something like this. Okay, so since these are just point loads, then the shear diagram will be something like this. And then the moment diagrams will be something like this. Okay, so so now let's look at the stresses. Okay, under light loads, and then if we increase these loads, what's going to be the stresses on this section, and then under heavy loads, what's going to be the stresses. Okay, so now let's cut a section. Okay, for example, this is the section that we cut, and then what's going to be the stresses. Okay, so we're looking at this, let's say side view or front view, and then let's say we'll draw this neutral axis. Okay, so under light loads, Under light loads, I will just write it here. Under light loads, so both concrete and steel carries the tension. Okay, so when you say under light loads, we're referring to tensile stresses below the cracking capacity of concrete. So we have the ones that's carrying the tension or the tensile stresses are both the concrete and steel. Okay, so if we draw the shear, the stress diagram, sorry, the stress diagram. Okay, so we'll draw here the steel reinforcement in dashed lines. Okay, so here we have something like this. Okay, so we have a, sorry, this is compression. Then let's say this is something like this, tension. Okay, so we have a uniformly, something like a uniform distribution or uniform stress distribution. Okay, we'll just use the color blue for steel. Then if we try to increase the loads, then what we get is the concrete cracks. So because concrete cracks, then the concrete can no longer support or can no longer distribute the stresses, the tensile stresses, because of the crack. So what's left is the tensile reinforcement or the steel reinforcement, the ones carrying the tensile stresses. Okay, so this is it. So we have F sub S. Okay, so we use Fs for strength of steel, and then we have this Fc prime for the concrete compressive strength. Okay, so this is under medium loads. Then if we try to increase the load some more, then we no longer have a uniform distribution, but rather what we get is something like a parabolic distribution. Okay, so again, this is the Fs, and then this is the Fc prime. Okay, so if we try to look at this in a three-dimensional view, what we're actually seeing is something like this. Okay, so we have these stresses. Let's say this is our neutral axis, and then this is our steel reinforcement. So we have stresses here. Okay, and then we also have stresses on this compressive, let's say compressive zone. Okay, so that's the stress distribution. Okay, so this is Fc prime, no, sorry, Fs, and then this one is Fc prime. Okay, so we can also look at this beam behavior when we try to look at the moment curvature diagram. Okay, so for this moment curvature, we have a moment along the y-axis and the curvature, let's say the rotation along the x-axis. Okay, so if we try to, okay, so looking back again here in this 2-point loading, so if we try to put a load on the beam, then we have a relationship between this moment and this curvature. Okay, so recall that curvature is something like this, slope. Okay, so at that point, what's going to be, what's the slope, or something like that. So below the cracking moment, then that's going to be something like this. But once the cracking moment is reached, then concrete cracks. So the ones carrying the tensile stresses would be the steel at this point. Okay, and then if you try to increase the load, then something like a behavior of steel, something like this. Okay, and then finally you get a fracture. Okay, so at this point we have yielding. Okay, so that's yielding of steel. Okay, whereas here cracking of concrete on the tension zone, cracking of concrete. Okay, so now let's talk about the code requirements regarding this reinforced concrete beams. Okay, so now we'll look at this stress block, this parabolic stress block. So recall that we have a parabolic stress distribution. Okay, and we are going to apply the equilibrium equations in this section. But if we have this non-uniform, let's say a parabolic stress block, then that's going to be difficult for computations. So there is a way to transpose this parabolic stress distribution into an easier, or let's say a handy way for calculations, and that's what they call as Whitney stress block. Okay, so Whitney stress block or rectangular stress block. Rectangular stress block. Okay, so if you try to draw the section, instead of having this parabolic shape, what we rather have would be a rectangular stress distribution. Okay, so in that way, we're gonna have an easier, or let's say a more convenient way for doing the calculations. Okay, so now let's take a look into the details of this rectangular stress block. So if you notice okay, so we'll compare the two, the parabolic stress block and then the rectangular stress block. So let's say this is our neutral axis. Okay, and then this is our steel reinforcements. So you would notice here that the stresses would be from the top face to this neutral axis. Okay, so that's going to be the stress distribution. But if we transform that into a rectangular stress distribution or rectangular stress block, then there's going to be some depth here. Okay, so it's not all the way to the neutral axis. So it's only from the top face up to some depth here. So that depth is what we call as the depth of stress block, and we designate that as A. Okay, so letter A. Okay, and if we go back here, you notice that, or let me try it again. Okay, so this is the depth of stress block, and then from top face to this neutral axis, or that's actually we use the symbol C, which means the depth of neutral axis, and then this distance from the top face to the steel centroid, that's what we call as the effective depth, or the depth D. Okay, so if we look at here in a three-dimensional view, then this is our depth of stress block, and then this is our neutral axis, depth of neutral axis, and then this point here is gonna be our effective depth. Okay, so I guess I'm running out of time, and we'll continue our discussion in the next video.